I think we can go ahead and start it. So we have our first talk of the conference here is by Sam Sanders from, so now you're at Volcom.
Exactly.
And so this is joint work with Norman on accountability of R. So thank you, Sam.
All right, thanks for the introduction, Andy. And yeah, thanks to the organizers for the invitation, of course, and setting this up and getting some moolah. So I should emphasize this is joint work with Dag Norman from the University of Oslo. Dag is often too modest, so he contributes a lot to this. And I'll be speaking today. So in one slide, higher order reverse math, you've heard of it. Of the uncountability of the reals. You've heard of the reals, yes, they're not countable. And so first thing I want to emphasize, and I will explain this in great detail, the usual definitions, countable set, injections, bijections to n, they don't really work in higher order reverse math. So that's the first thing we'll be studying. And the literature luckily has alternative definitions that do work. And you get lots and lots and lots of equivalences, which includes new big systems, as one might say. And these equivalences are from mainstream math. We're talking about bounded variation, rectifiable curves, and yeah, very basic real analysis stuff. My first supervisor sometimes said I'm almost an analyst, but actually a logician. So, of course, now you wonder why in particular the uncountability of the reals. Sure, it attracts the crackpots sometimes, especially that diagonal proof. But the uncountability of the reals is special in higher order reverse math, and special in a good way. So for that, we should go back, to explain this, we should go back to basics. So what are the beginning? What's the beginning of reverse math? Some inspiration must have come from all the equivalences of the axiom of choice. ZF cannot prove the axiom of choice, and it has plenty of equivalent formulations, and the same for fragments. Now, the axiom of choice is special. So this first book, by the way, by Horst Herrlich, it's herrlich to read. It's really nice to read. And yeah, so there's books on the axiom of choice. It's famous. It's even famous in popular mathematics, XKCD. I don't know if you can read that. So the axiom of choice is special. Why? As already noted by Borel, Baer, Lebesgue, Hadamard, and these men, the choice function is fundamentally non-constructive. And so we actually, when we have a theorem of ZFC, we actually ask the following questions. It's two-dimensional. Is the theorem T of ZFC provable in ZF alone? Or if not, which fragment of AC does T imply? This is a very basic observation. And today, what am I peddling? I am peddling the observation that exactly the same thing happens in third order arithmetic. The same two-dimensional picture. Namely, let's say we have S, a theorem formulated in the language of third order arithmetic, ordinary math. And we ask ourselves, or we should be asking ourselves the following questions. Is S provable from conventional comprehension alone? Conventional comprehension and its higher order counterparts, you know. That's what second order arithmetic is based on. There's also a higher order counterpart, which historically came first, which I will also explain. Now, this is the first question. The second dimension is the following. First of all, can we prove it based on comprehension alone? And if not, which fragment of the neighborhood function principle, NFP, does S imply? Now, what is NFP? You can find it in Troelstra and Van Dalen. NFP is a fragment of the axiom of choice, provable in ZF, with continuous choice functions. If you're ever to have a Platonist revelation, please have it now. The foundations of mathematics, ZFC, have a certain two-dimensional nature to them. Third order arithmetic has exactly the same two-dimensional nature. And the second dimension is also a fragment of the axiom of choice, but with continuous choice functions. If that is not beautiful, I don't know what is. So, and now comes the uncountability of the reals. It is in fact the weakest natural third order theorem not provable from conventional comprehension. So, I mean, you can't, of course, prove that because it has the word natural in there. Natural is a subjective term. I hold that the fact that the reals are uncountable is natural, and we will see many natural equivalences in higher order reverse math. All right, so that's the first part. Now I will explain that in more detail, obviously. So higher order reverse math, voila, which means lo and behold in French. Ulrich Kohlenbach wrote a paper on that in Reverse Math 2001. So what's the idea? As you know, a second order reverse math only has variables for the natural numbers and sets of natural numbers. The rest has to be represented or coded, functions on the reals, metric spaces, and all other assorted good and plenty. The idea of Kohlenbach was actually rather utilitarian. Just use the richer language of all finite types and cut down a little on coding. It did not mean any offense, but yeah, some people did take some. What is nice, for example, you have direct access to discontinuous functions on the rails. They exist, they predate set theory by hundreds of years. And they do. And yeah, so that was the idea. And Harvey Friedman, in a lively FOM discussion, has proposed a different framework. You can use this framework, why don't you? But the same picture based on NFP would emerge. So Harvey Friedman's framework and Kohlenbach's framework will give you the same picture based on NFP. Yes. So, since you may not be entirely familiar with higher order reverse math, I'll discuss the base theory a little bit. So the language of finite types has the objects you know and love, the natural numbers, or type 0 objects, first order. I would now write this on this flip chart. First order natural numbers, type 0 objects, elements of the Baire space, type 1. And then comes something new, type 2 objects, mappings from Baire space to the natural numbers. And once you have that, you can define mappings from Baire space to Baire space, and so on. So, of course, there's more. There's fourth order, fifth order, but we'll just be talking about third order today. Third order really means mappings from Baire space to Baire space, or Baire space to N. And then, of course, you can have functions on the reals. The base theory includes, of course, basic axioms. Here we have a mapping from Baire space to N, and identical inputs should yield identical outputs. This is called function extensionality. It's very basic, that's why it's among the basic axioms. Primitive recursion for elements of Baire space, you may have heard of that once or twice in the base theory of reverse math. Induction for quantifier-free formulas, so a formula is quantifier-free if it's free of quantifiers, except maybe bounded quantifiers over the naturals. And then comes the Swiss Army knife. So this is a little bit of axiom of choice, provable in ZF, of course. And this gives you delta 0, 1 comprehension. It gives you sigma 0, 1 induction. And it gives you coding. What do I mean coding? Third order objects are represented in second order reverse math. And the statement, the following set codes a function from reals to reals, or say from Baire space to Baire space. You can write this as this kind of formula. And then there's a third order object that equals the outputs of your code everywhere. So again, this or that set codes a third order object. You can write as this kind of formula. And then this G is the actual third order object you're representing. So all that effort everybody's been doing, coding very hard, well, this axiom says, well, actually, it's also actual third order things, or type 2 as, because it's a type theory, because yeah, computing happens with types generally. So that's the...
Y, in this formula, Y is,
Yeah?
what does the Y stand for?
Well, any type 2 object.
So Y is already a type 2 object, and the axiom is asserting the existence of another type 2 object.
Exactly.
Is exist any in the conclusion of it?
Exactly. So imagine F is the input of your code, N is the output of your code, then G. And primitive recursion allows you to write this Y down, of course.
Term.
No, it doesn't have to be a term. No, you can just quantify over the Y quantifier can be outside. It doesn't have to be a scheme actually. Anyway.
Quantifier, dummy quantifier,
Yeah, that's oopsie daisy. That's not there obviously because there's no N. All right. Now, what is important? RCA0 and RCA0 little omega give the same L2 sentences. This is proved using the ECF translation, which I would also write on the slide now. And the real numbers are fast conversion Cauchy sequences, as you know from RCA0. Functions from real to reals are functions from bare space to bare space with the right coding, and they have to be extensional relative to the real equality. And that's basic. If you have two reals that are equal, the outputs have to be the same real as well. So it's really just, I mean, they prove the same L2 sentences, they use the same approach to real numbers. It's all very the same, except that it's third order and more. So Harvey Friedman, and I guess by extension Noah Schweber, they cut everything off at type 2. They just say now we only look at third order objects. You can do that. Everything I'm going to tell you carries over mutatis mutandis, except for one thing which I will point out. So now,
with second order logic, there's really an intended model.
Come again?
With second order logic, reverse map, there's an intended model. The natural is the power set of omega. So I guess your natural model is going to be power set to the power set.
You mean the full model, or?
Yeah, the full model.
Yeah. Well, you can also take ECF actually refers to the canonical model of type theory where all operations are continuous. So all these.
Is there a nice way to describe that?
Everything is continuous. Is
with second order logic, you have a nice model, right? The natural to the power set of omega. Where's your nice model?
Can we discuss that offline? So nice model. Yeah, you can go for the full model, or as I said, you can go for the canonical model of type theory. Like all these type theories, Koch, Agda, etc., they're consistent with all functions are continuous. All functions from say reals to reals. That's sort of that's a nice model, and that's like rec for say.
Well, let's talk about it more about.
Yeah.
I mean, with second order logic, right? You look in some fragments, some power set, something that takes to replace a power set, right?
Yeah.
That's easy to understand, theoretically. I'm a simple guy, so you understand it that way.
All right. So Dak would say Dak thinks in terms of full ZFC. Otherwise, Kleene recursion theory doesn't work as advertised. So, well. So, higher order comprehension, actually going back to Hilbert and Bernays. So, Kleene's E2 is essentially higher order arithmetical comprehension. Here you have it. So, it's a third order object. And it takes as input an element of bare space and decides if it has a zero or not. So essentially here, this sigma 0, 1 formula can be replaced by a quantifier free formula. And you can repeat this and remove any arithmetical quantifier. As clean as E2, it's discontinuous at 1, 1, 1, 1, 1, obviously. And so yeah, there you have your discontinuous function, and this is arithmetical comprehension. So in Hilbert Bernays' Grundlagen, they formalize mathematics. They have 3 systems: H, the biggest system for Hilbert; K, where they use Hilbert Bernays' mu operator, or Fefferman's mu, which is essentially E2. So Hilbert and Bernays, their second system was formalizing lots of mathematics in essentially arithmetical comprehension based on this puppy right here. Actually, the mu operator, but yeah, that's essentially the same. So Hilbert and Bernays, yeah, they never touched ACA0 essentially, but they did use this to formalize lots of math. So Ziege and Pfefferman have introduced, again, essentially S2K, which decides Pi1K formulas. You know Pi1K form comprehension? Now you have a third order object that takes as input the right code, let's say, for a Pi1K formula in cleanly normal form, and tells you 0 or 1, depending on whether this holds. So E2 can decide arithmetical formulas, and then there's S2K that can decide Pi1K formulas. The hyperjump is also called the Suslin functional. It can decide Pi11 formulas. Pi11 comprehension is, of course, a big thing. And yeah, then Pi1K comprehension omega is just the base theory plus S2K. And Z2 little omega, you throw everything together. Then here is the part that Harvey will not speak about. Oh no, not yet. So this is all conventional comprehension. When I say Pi1K, I mean only first and second order parameters, because yeah, things are what they are in the third order world. So Hilbert and Bernays formalize most of their math in system H for Hilbert. And they use this nu operator, which is essentially Kleini's fourth order E3. So it can decide whether this third order object has a 0 or not. So here we have a quantifier over bare space, and it just gets removed. So this gives you full second order arithmetic in one fell swoop. E3 can decide any formula with a quantifier over bare space. Nonetheless, they are all conservative over one another, so over the L2 language. They all prove the same L2 sentences. This was proved by James Hunter in his PhD thesis under Stefan Lemp at the University of Madison, Wisconsin. So, sure, this is a fourth order object. However, Hilbert and Bernays used it. They never really used comprehension. They mentioned comprehension once, and then they say you could use this to formalize math, which they don't. But so they do mention comprehension. So some people have missed that over the years. Comprehension is written with a K, however, because it's German. But so Hilbert and Bernays use mostly higher order stuff, but it doesn't matter because it's all conservative if you look at Z2. All right, so history lesson over. Let's go back to some math. First set theory paper, Cantor 1874, the uncountability of the reals, can be formulated in a number of ways. You could say, Cantor's theorem, there's no surjection from n to the unit interval, or you could say there's no injection or bijection from the unit interval to n. In a sense, these are weak, the last two. NIN and NBI are weak, where I credit our study of NBI to Carl Mummert and Jeff Hurst, who suggested it actually. It's been very interesting. And half of all third order theorems imply NIN or NBI. And so, yeah, Dagnoman and I have a huge list. It's published in the JSL 2022. So there's so many, even with a name, Jordan decomposition theorem, Arzel's convergence theorem for the Riemann integral, and lots of covering theorems, Vitali, Heine, Borel, Cousin, which were of course originally formulated for uncountable coverings. So many of those third order theorems imply the uncountability of the reals. So this is really the weakest principle. We couldn't find anything that's weaker than NIN or NBI. So this basic fact is really supremely weak. So yeah, it's supremely weak. It's also supremely strong. Z2 little omega cannot prove it. Z2 big omega can. Recall they proved the same L2 sentences. And yeah, Z2 little omega is based on third order functionals S2K deciding pi1K formulas. And NIN and NBI are also third order because you say for all mappings from the reals to N, which is a third order statement. So we're comparing apples and apples here, or oranges and oranges. Now that's of course, how did that happen? Z2 little omega can't prove it. Z2 big omega can prove it. And so this weak principle would be at the level of Z2. And, yes, this is important for the Arno Paulis of this world. You present this kind of result. People ask questions, not always in the most nice way. One criticism is, yeah, but you quantify over all third order objects for any mapping from the unit interval to N. Yeah, we do. That's bad somehow. Note that NIN can be restricted, and yeah, there is no nice injection from the unit interval to Q, where nice can be Borel. The usual definition of Borel, I'm not talking about Borel codes. When I'm talking about Borel codes, you will know because I will say the word Borel code. So just the definition of Borel, you can say, well, there's no Borel injection from the unit interval to Q. There's no bounded variation injection. There is no upper semi-continuous. There's no quasi-continuous, and so on. So yes, sure, NIN here quantifies over all mappings, but you can restrict it to nice mappings. So that criticism is, well, null and void. And this is an equivalence over, say, RCA0 omega. Or much less if you want, probably. Very basic stuff. Like if you would have RCA0 omega star, so not primitive recursion, but only the exponential function, you could still do it, I guess. Right, so now, in physics, not a day goes by when people find something wrong with the standard model. The standard model is still with us. So what do you do if you find your classification has problems? You try to extend it, and that's what we do. So these intuitively weak principles are classified as rather strong on the scale of conventional comprehension. So then we just, we extend our model, our theory, and we need a classification where weak principles like NIN are also classified as weak. And this is this NFP I have been talking about. Ironically, Brouwer comes to our rescue. Luitsen Egbertus Jan Brouwer, Bertus to his friend, is infamous for intuitionism. He was also Scandinavian, like my family. You know that intuitionistic logic can be formalized via intuitionistic logic and non-classical continuity axioms. Because Brouwer could prove that all functions are continuous, the canonical model of type theory. Now, these continuity axioms, they have a non-classical weak counterpart. So there's continuity and there's weak continuity. How do you connect them? NFP. So Kreisel, Troelstra, and Van Dalen have looked at this. NFP is classically valid and it connects Brouwer's strong and weak continuity axioms. And here it is. Here you go. So it has a definite choice aspect to it. For all there exists, then there is a choice function. So gamma in K0 means that K for Kleene means that gamma is a Kleene associate, which you know as reverse math code. Of course, when Kleene was alive, reverse math codes didn't exist yet. They were called Kleene associates. But so gamma represents a continuous function, and it is a reverse math code. So it's essentially, as I've said, the axiom of choice. For all there exists, then there's a choice function. It's important to note that here f only occurs cut off at n. That's why you can have a continuous choice function. Otherwise, yeah, things would be non-classical. So this is NFP, the axiom of choice, some fragment of the axiom of choice with a continuous choice function. And the point is, you can prove full NFP in ZF. You don't need the axiom of choice beyond ZF. And Z2 little omega can't prove even the slightest fragment of NFP. So it's rather orthogonal. And this is the same as saying, well, choice functions are non-constructive. In ZFC, choice functions from AC are very non-constructive. Here, the same thing. This gamma is extremely non-constructive compared to Z2 little omega. And many third-order theorems with a name, like some are there, imply or are equivalent to such fragments. So I should get this published actually, but the Heine-Borel theorem is equivalent for uncountable covers, is equivalent to a nice fragment of NFP. So NFP where you have one quantifier over bare space here. And of course you allow for third order parameters. So there's that. And NBI, there is no injection from the reals to N, seems to be the weakest fragment of NFP, as far as we know. So this is NFP, fragment of the axiom of choice, and this brings us to this grand two-dimensional higher order reverse math. So I'll repeat my point. ZFC is two-dimensional. The axiom of choice has a central role. And we should be doing higher order reverse math in actually exactly the same way. We have conventional comprehension is one dimension, and NFP is one other dimension. It's similarly two-dimensional, and this is how it works. If you replace all your third order objects by codes, the two dimensions collapse. So having third order parameters around gives you this two-dimensional picture, just like for ZFC. If all you do is second order encodes, these two collapse. And the uncountability of the reals, again, is the weakest principle you cannot prove in Z2 little omega. Don't ask me how you build such a model. I can explain it to you, but that requires some explanation. So that's that. Now let's do some actual reverse math. So this is the background. This is the way you should be thinking. You already know, well, when we analyze theorems, we look at how much comprehension or fragments we need. Here there's a second dimension. If you want to get into this, this is the way it is. Now, our next big system, the Jordan decomposition theorem. So Jordan introduced the notion of bounded variation. Why? Dirichlet had proved some convergence theorems for Fourier series. Unfortunately, that was rather limited because Dirichlet's results, the functions can only have finitely many points of discontinuity. Essentially, Euler already wrote down the notion of function we use today, and Euler and the gang talked about discontinuous functions as we use them today. And Dirichlet was trying to do Fourier analysis, but got stuck at finitely many points of discontinuity. So he was saying, yeah, piecewise continuous is fine, but I can't do anything else. Jordan said, look, here is the notion of bounded variation, and the Fourier series converges. So Jordan proved many interesting results, including that BV, the class of bounded variation functions, is exactly the class of rectifiable functions. Rectifiable means the arc length makes sense and is finite. So an arc length, the idea of you draw a curve, what length does it have? The first reasonable definition can be found in 1866, and in 1833 they were close already. So this has a rich history, all predating set theory by our lifetimes. Now, so what is bounded variation? This is bounded variation. A function has bounded variation if there's some upper bound k0 on all these sums. So any partition, there's an upper bound for any of these sums for any partition. That's what it means to have bounded variation. And this can't happen is essentially what bounded variation means. It can't fluctuate too hard. The total variation is defined as this supremum, which may or may not exist in RCA0 little omega. So when I say bounded variation, I mean this definition, which was the original one used by Jordan, by the way. For example, Weierstrass's monster function, which is continuous but not differentiable anywhere, is not in BV. So we're really like just above continuous functions, literally. This is like real analysis 101. And so, for example, bounded variation functions are regulated. The left and the right limits always exist. And you can compute them using Kleene E2. So if you have higher order arithmetical comprehension, these limits always exist. And that's a good sign, which means we can study the notion of bounded variation and regulate it. We can study this in ACA0 omega. That's a good sign. And again, this insight is due to Dach-Neumann, for example. So and then Jordan proved if you have a function of bounded variation, it's actually very simple. It's the difference of two non-decreasing functions. Very basic. And of course, the third order Jordan decomposition theorem implies NIN, that the reals are not countable. So Z2 little omega cannot prove third order Jordan decomposition theorem. That's actually quite easy to prove. Now, people have looked at second order versions of JDT with codes, second order representations, and invariably you can prove everything in ACA0. I'm talking about Andre Nice's papers, Alex Kreutzer, and so on. So you can see how coding or not coding does make a difference here. And so this also tells you why we're interested in NIN. It's a kind of Swiss Army knife. If your theorem implies NIN, you know that it's in. You have to start digging in the NFP hierarchy. So we've studied the higher order reverse math of the Jordan decomposition theorem, and nothing worked. It was frustrating. Like, we have a cool principle, but we can't find any equivalences. Why? Yeah, why exactly? And the reason is, here's our first problem. This set is central to most of the basic real analysis, the discontinuity set. This is the set where f in BV is discontinuous. Namely, the right limit does not equal the function value, or the left limit does not equal the function value. You can define this set in ACA0 little omega. And as I've said, it's central to all of real analysis. But you can't do anything with it. It is countable, but you can't find an injection. So sure, this set is countable, but let's get an injection. Nope. There is no way in hell you can define an injection, even if you assume this is Z2 little omega. So you can't say anything about this set, and all the proofs from real analysis don't go through. And it gets worse. Yes, and for regulated functions, which is a bigger class, you have the same problem, obviously. Now there's a second problem. The discontinuity set is, of course, F sigma, and here it is written as a union of closed sets. df equals the union over k of dk. And dk is the point, all the points where f is discontinuous and the jump is in excess of 1 over 2 to the k. This is a finite set. Yeah, so it's finite, so give me an injection to some finite set of naturals. Doesn't work. Nothing works. Frustration. And also this set is of course closed, but you can't find a reverse math code. You can't find any constructive enrichment. And so yeah, frustration. So the usual definitions of countable and finite set don't work. Try as we might, we can't work with them. So what do? Well, we look for different definitions of countable sets as we do in reverse math, right, gentlemen, ladies, everyone? So the solution is already here. Namely, this set is countable and it's a union over n of finite sets. And that you can find in the literature. It's called height countable. So a set is countable or height countable if there's a height function. So instead of an injection, you have a height function. And an is all the elements of a where h of x is below n is finite. So you can find this in the literature here and there, the notion of height function, in textbooks, even like Royden's real analysis, he uses height functions in the 4th edition. And so this is equivalent, say, over ZF, this is equivalent to being countable, and this is the right definition. Union over n of finite sets. And you do need a specific definition of finite set too. So again, forget about injections, they don't work. A set is finite if it has an upper bound n, such that for any finite sequence of n elements, of reals, there's at least one that's not in the set. That is the right definition of finite set in higher order reverse math. And now we can reverse. So you have to pick the right definition of countable, you have to pick the right definition of finite set, and then we can reverse. So the following are equivalent over, say, arithmetical comprehension. A height countable set can be enumerated. Well, of course, it's countable, so there's a sequence for it. And this is the same as for regulated functions enumerating the points of discontinuity. There's only countably many, they're height countable, and it doesn't matter if you use the unit interval or the real numbers. And then you can have the Jordan decomposition theorem on the half line. So you have a function that's of bounded variation on any interval, and it can be written as the sum of the difference of two increasing functions on the entire half line. Then you need the finite union theorem, which says that a finite union of finite sets is finite, which follows by induction. But I mean, it's, yeah, you need that. And you can go down more. You can have the Jordan decomposition theorem on the unit interval, but then you need the uniform finite union theorem, which tells you that you have some sort of upper bound on your finite union always. And so there's lots of equivalences. Even Sierpinski's theorem, a regulated function can be written like so. So lots of equivalences. For example, this, a non-enumerable and closed set of reals has a limit point. Sets are given as characteristic functions, like they are in measure theory and probability, of course. Lots of equivalences, and really, really, really lots of them. Why? Bounded variation is sort of just above continuity, and then there's regulated, and then there's oodles of spaces in between. People write books about that, as you can see. It's a nice book, it's well written. I only found one mistake in one proof somewhere. So, and the same holds true for rectifiable functions. All the stuff I've said you can do again for all these intermediate spaces. And there is really a fuck ton of them, and a metric unit that is. So yeah, many equivalences. So Dacia and I will publish this soon. many equivalences for the Jordan decomposition theorem, and it's really nice. Like, some notes are in order. So yeah, you have to work over this. We're lazy, we work over a strongish space, and you can probably do much weaker. Like, you don't always need the axiom of choice, you don't always need arithmetical comprehension, but we wanted to go fast. We move fast, we break things. You can replace the finite union theorem by basic mathematical facts as such. If we have f1 to fk that have bounded variation, the sum has bounded variation. It's a basic fact, and it can replace the finite union theorem, which is nice in all the previous. There's probably many similar mathematical facts. Sometimes the details get messy. I leave that to somebody else. What is nice? Pi11 comprehension, omega, so the Suslin functional. Again, I would write that on the flip chart. So this system is pi13 conservative over pi11 comprehension. If you add the Jordan decomposition theorem for the unit interval, boom, you can prove pi12 comprehension. It's an explosion, we call that. So you see that the reason why comprehension and NFP are sort of orthogonal, if you put them together, you get this. Logical strength explodes, because Michael Ratchin and Per Martin Löw, they would say, well, pi12 comprehension dwarfs pi11 comprehension. There's a chasm, an abyss, and other AP words. So, but what you need to bridge this gaping maw, the Jordan decomposition theorem. It takes you from higher order, pi11 comprehension, to pi12 comprehension. Isn't that beautiful? Now, before somebody asks, you can demand that this supremum always exists. So I just worked with the normal definition of bounded variation. You can say, look, let's restrict everything to this supremum always exists. You can. And many of the equivalences go through. You just have to throw away injection and height function and replace that by bijection. So bounded variation is bounded variation, and as we know from reverse math, if we demand that such a supremum exists, you get a lot weaker principle. It's still slightly explosive, and height function is out of the window. You have to use bijections. So just for the record, this is not terribly interesting, but it does exist. Yes, well, here why is it interesting, and I'm going to be as neutral here as I can be. So the Jordan decomposition theorem can be formulated for functions for which this supremum exists, and it exists at the level of hyperarithmetical analysis. So a third order Jordan decomposition theorem, where you demand that this supremum always exists for all functions. This is rather weak. It exists at the level of hyperarithmetical analysis, and some philosophers would say this is perhaps more natural than set theoretical principles that are generally studied there. I'm blaming it on the philosophers. So the conclusion is that, as I've tried to argue, if you want to go in the wild west of higher order reverse math, and you want to study bounded variation, which is slightly above continuity, the usual definitions don't cut it. There are alternatives, they are from the literature, and they work very nicely. We need this bespoke definition of finite set, equivalent, say, over strong systems, but we get many equivalences, as I've shown you. And it's really many, because there's so many spaces between the regulated and the bounded variation functions. We've, of course, studied this first in Kleene's recursion theory, based on S1 to S9. That is extremely robust. The associated higher order reverse math is rather robust. It's not as robust, but it's nice. And we've been talking about points of discontinuity, like the Jordan decomposition theorem essentially gives you a list of points where a function is discontinuous. What about points of continuity? Because why not? And that brings us to the uncountability of the reals. Again, surprisingly. So we want to study the following notion. The unit interval is not height countable. Height countable essentially means a union of finite sets. So the unit interval is not the union of finite sets. You may think this is trivial, but it's not. It's the weakest fragment of NFP, not provable in Z2 little omega. So again, height countable means that. This definition comes from the literature, Royden 4th edition Real Analysis. And there's no equivalences if you use injections or bijections to N. Again, this is the right definition for equivalences. So the unit interval is not height countable, is basic principle. So again, the base theory, you can probably have a much weaker system. You don't need arithmetical comprehension. I leave that to somebody else to figure out. For example, this is just reformulation of the definitions. If you have a union of finite sets, the complement is non-empty. Well, sure. The complement is actually dense. That's still equivalent. The complement is not height countable. There is no injection to N. There's no bijection to N. They're all equivalent. So it has a robustness, which is nice.
Sam?
Yeah?
Is that finite in your sense?
Yes. Yeah, it's all. When I say finite, I mean this bespoke definition. That's finite in, Yeah, I struggle to find a good word for that. I mean, you could say, usually I say when injection to finite set of natural numbers, that's set theory finite. Because there's also Dedekind finite. And this is, third order arithmetic finite, and this is equivalent to, for a regulated function, there is a point where f is continuous. I bet you didn't see that one coming. The fact that the unit interval is uncountable is equivalent to a regulated function has at least one point of continuity, or a point of quasi-continuity, or lower semi-continuity, or any of these millions of notions of continuity they've been studying in topology. Or the continuity set can be dense in the unit interval, and it's still equivalent. You know, when I say robustness, I mean it. And so Antonio cornered this notion. It is a very nice concept. And for example, the continuity set is not height countable, or not countable, not enumerable. These are all equivalent, which is nice. And consider the negation of the fourth item. There is a regulated function. Wait a second. The fourth item. That is discontinuous everywhere. The entire edifice of analysis just collapsed. Analysis is a big deal of analysis is you have these spaces and how continuous are functions and properties. And so the reals are uncountable is equivalent to, there's a regulated function has a point of continuity. If the reals would be countable, all of real analysis would just collapse because there would be a function of bounded variation or a regulated function that's everywhere discontinuous, like Dirichlet's function. And so there's a conceptual reason why the reals are uncountable, namely because analysis works. As the engineers, it works great. Now, oh, I thought there was a joke there, but no.
Wait, the second to last item looks strange. Regulated f is pointwise is continuous?
Pointwise discontinuous, that means the continuity set is dense in the unit interval. That's just a definition. So the pointwise discontinuous is a notion that was defined by Henkel, a student of Riemann. And it means the set of continuity points is dense in the unit interval.
Why is it called discontinuous then?
Go ask Henkel, he's been dead for 300 years, but. So pointwise, it's called pointwise discontinuous, I don't know why. So the big point here is, and I hope this is not offensive to anybody, you have the Baire hierarchy, Baire 1, Baire 2, and so on. And the pointwise discontinuous functions are sort of orthogonal to that. They don't really align well with the Baire hierarchy. So for conceptual reasons, this is a very difficult concept, and people just chose to sort of, let's just ignore it. Let's just go for the bare hierarchy. That's my best explanation. So I could have gone with Volterra, Vito Volterra. So what's the history here? So yeah, Riemann's integral was revolutionary. Why? Before Riemann, you could only integrate functions that have finitely many points of discontinuity. Riemann's integral allows you to do more. And Tomai, this guy, even defined a function, Tomai's function, has many names. It's continuous on the irrationals and discontinuous on the rationals. So here we have a function that is Riemann integrable, but it has a dense set of points of discontinuity, namely the rationals. And then you ask, of course, yeah, what's the dual? And Volterra showed that there is no dual. There is no function that is continuous on Q and discontinuous on R minus Q. So that's student Volterra, his first paper. And this is usually proved using the bare category theorem, but you can prove it without. And then the following are equivalent. Volterra's results are all equivalent to the unit interval is not height countable. So here we have Volterra's corollary for regulated functions. There is no regulated function that is continuous on Q and discontinuous on the complement. That's Volterra's corollary. Volterra's theorem is also equivalent, again for regulated functions. So this sort of, and there's many generalizations, people have generalized this, and all this stuff is equivalent. So the unit interval is uncountable in the sense of height countable, is equivalent to Volterra's results for regulated functions. So this is very standard real analysis in many ways, and it's equivalent to the uncountability of the reals over arithmetical comprehension, let's say. And now I'm just going to knock you dead with a lot of equivalences. So the unit interval is not height countable is equivalent to this basic property of regulated functions, which you can find in Bourbaki. A regulated function has a Riemann integral. Suppose it's 0. Then there is one point where a function has to be 0 at least. This is the most basic property of the Riemann integral. If it has a 0 integral, it must be 0 AE. But one point is enough to get you the uncountability of the reals. Blumberg, he proved that every real-to-real function is continuous on restricted to a dense set. And Blumberg's theorem for regulated functions is equivalent here. And so, the fundamental theorem of calculus, yay! FTC. A regulated function, this primitive exists, and there's at least one point where it is differentiable and the derivative is f of x0. That's equivalent to the reals being uncountable. Isn't that pretty? And any regulated function has a Darboux point, a point where the intermediate value property holds. And you can, so here we have, it's all robust. Here we have one point where it is 0. There's actually a dense set, or the set where f is 0 is not height countable. All these modifications are possible. It's extremely robust. And now comes my joke. But don't say the M word. I will say the M word once. Measure. This is extremely robust, but don't mention measure. Lebesgue measure. Once you measure positive or measure 0, all the equivalences break down. It's extremely robust, but you have to stay in the bare category part of the world. Density, uncountability, cardinality, it's all fine. All these notions, there's extremely robust, but do not mention measure. Measure and all these equivalences break down. So that. And then you will ask, of course, oh, Sam, but you try to sneak something past us. This is all for regulated functions. What about bounded variation functions? Well, actually, then we need another notion of countability, namely height and width countable. This is still slightly stronger than injection to n. A set is a height and width countable if there's a height function, such that this Bn has size at most Gn. So the height function you have these finite sets, they have a height, and there's a width function. They can't go too far, they can't be too, the girths or whatever you call it can't be too wide. You have to have a bound on how big these finite sets grow. And that's height and width countable. It's still slightly stronger than injection to n. Because with an injection, if h is an injection, Bn has size at most n.
What is h of,
That thing shouldn't be there somewhere.
Okay.
So I seem to have used an old version of my slides, unfortunately. And then you have plenty of equivalences. For example, the unit interval is not height and width countable, is equivalent to, for a function of bounded variation, there's a point of continuity. So you need exactly this definition to get the equivalence, nothing else. And you can recycle all the previous stuff. Regulated is replaced by BV or generalized BV. So imagine 20 equivalences now. But here is a proper equivalence. A function that is bounded variation. There is a point where the Fourier series converges to f of x. That's like basic analysis. And that is exactly equivalent to the unit interval is not height and width countable. And this is actually false for regulated functions. For regulated functions, the Fourier series can do whatever. Quelconque, I think the French would say. And here is something pretty, one of my great loves. An unordered sum is a way of, you have a sum over uncountable sums. Some more perverse minds like to think about these things. Can we, we know series, can we give meaning to sums over uncountable sets? Of course, if this makes any sense whatsoever, you know that this has to be zero except for countably many points. And so if this sum makes sense, then there is one x such that f of x is 0. And so this is equivalent to the unit interval being uncountable. If the unit interval is countable, these uncountable sums always make sense. Which makes sense, right? In a strange, perverse way. And the negation of the fourth item is again very bad. If the unit interval would be countable, then there would be a bounded variation function where the Fourier series converges nowhere. Again, all of the carefully crafted analysis comes piling down. So we really need to assume this. However, all this stuff you cannot prove from conventional comprehension. All this stuff has to be proved from NFP. It's actually the weakest fragment of NFP. And how much time does the chair allot still?
You can keep going a little bit, yeah.
All right, so a couple of slides still. So this is big in the future. So we've done the bare category theorem in Kleene recursion theory. We actually have an equivalent model of the lambda calculus. So S1 to S9 is equivalent to some nice model of the lambda calculus. So, and I'm saying all this should be equivalent. I'm not saying it is, but I think so. So the bare category theorem, if you have a sequence of open dense sets, the intersection is open and dense, it's dense, sorry. This is equivalent to if you have a bare one function and its oscillation function, then it has a point of continuity. All the other stuff is also equivalent. Just throw out regulated and look at bare one, upper semi-continuous, even small bare classes you can look at. Everything is equivalent. But you have to look at bare one functions and the oscillation functions. What are oscillation functions? This goes back to Henkel again. So people were trying to give some sort of integrability criterion for the Riemann integral. And that's where the Lebesgue measure comes in. But Henkel tried to do it using this construct, the oscillation function. And so the bare category theorem is equivalent to a bare one function that comes with an oscillation function is continuous somewhere. And it's equivalent to everything I've been talking about, but for bare one functions, or upper semi-continuous functions, or any small bare one class. So you have my countryman, Bourgain, has introduced a hierarchy for the bare class, bare one, based on ordinals. You can take any ordinal, you can cut it off anywhere, and still you will get this equivalence. So reverse math is not particularly interested in this bare one hierarchy, it's just all equivalent. We know that it's equivalent computationally. I think it should go through for higher order reverse math. Bare one isn't such a nice construct, it's difficult to get a hold on, but that's why we have this oscillation function. It's a constructive enrichment we need, what that goes back to Henkel 1870, whatever. So, I'll just skip what I was going to say on coding because nothing good can come of that. Thank you very much.
We have a couple of questions, either from the room or from the chat.
Maybe you have to upgrade the participants then?
Yeah, they'll tell me if they want to.
All right.
Yeah, if anyone from the chat wants to ask a question, just let us know on the chat.
So I have a question. How long did I take?
31 now, so 1 hour and 1 minute.
All right.
So, can I ask?
Yeah.
So, what's the rule of sigma 1 induction in this third order reverse mathematics?
Sigma 01 induction?
Yes, yes. So I'm asking this because in second order reverse math, the strength of the induction scheme is central to the study of a number of problems involving combinatorial mathematics. And so using the analysis of Ferris-Kirby, we have non-standard models of various of different inductive strength and so on and so forth. And that information has provided a lot of insight into the strength, the first order strength of theorems of combinatorial mathematics. Now, in the case of third order, do you have something like that?
That's actually a very good question. We have sometimes you don't need induction. So there's some equivalences that would go through over nothing almost, and sometimes it seems you really need induction. So sigma 01 induction or more. So when I mentioned the finite union theorem, this is one of those things that I think actually has an equivalent formulation in terms of induction. So sometimes induction seems really essential. So exactly the same thing seems to happen here, but it's mostly unstudied. Many of these equivalences would not go through without some induction somewhere. And for example, this finite union theorem is an example. And you can sneak it in, of course. So this, of course, is you sneak in induction one way or the other. If you have finitely many functions in BV, then the sum is in BV. This is best proved using induction. It's probably equivalent to some kind of induction. And yeah, so let's say half of the time we don't need induction, half of the time we feel like we really need some induction and we disguise it sometimes. Actually, a very good point, yes. There is an induction principle that is equivalent to the following. If a set is set theory finite, so there is an injection to some finite subset of n. If a set is set theory finite, it is my kind of finite. This is equivalent to some kind of induction principle, and you need it here and there. So I think you have a similar rich study of induction you could do. It's just that, yeah, what are the tools for it? But so it's a very good question. I've sort of hand waved a little, but so yeah, here, for example, induction is hidden. And half of the time, I think you need it. So yeah, thanks for the good question.
So there is a comment from,
Just a follow-up on that.
yeah, okay.
Yeah, would you happen to know to which induction principle this would be equivalent between the fact that the usual definition of finite and your definition are equivalent?
Yeah, I can tell you later. It's also the Bolzano-Weierstrass theorem in some form or other also lives in that neighborhood. So if you yeah. So yes, exactly. I can try to explain it to you. So no, that would work. Sorry. We have time. I can explain it also.
Okay, Harvey, you have a question.
Yeah, well, I have a question comment. If I go back in the way I look at reverse mathematics in the 70s and earlier even a little bit, the main conception I had was what I call now strict reverse mathematics. And I'm giving a talk on that tomorrow. And here in strict reverse mathematics, the idea is that first of all, you don't allow, ideally at least, you don't allow any coding. And the second point is that you don't use base theories or infrastructure that has any kind of extra mathematical flavor. In other words, ideally, everything you look at is from our statements from the mathematical literature. Now, obviously, the standard RCA naught even, the standard second order RCA naught even, does not satisfy that criteria. And what I did in 1976, I don't think that anybody remembers even, except me, is that I gave a version of RCA naught, which was strictly mathematical, and had that everything, at least arguably, every single sentence is in the mathematical literature. Now, this puts a certain discipline on everything that is generally not done, but if you do adhere to this discipline, you really have quite a different subject in a lot of ways. And particularly as you go up in complexity of the mathematical objects, the removal of coding and the removal of any logically oriented infrastructure changes everything. Everything has to be redone and rethought, and issues and problems come up that you wouldn't have normally thought of. So I'm suggesting, one we'll see in this talk, first of all, a reworking of the whole of reverse mathematics along strict mathematical lines, although that's not as radical as it sounds. For much of this, that would be fairly straightforward. But once you get involved in continuous functions or even real numbers, even just real number line and various things like that, when you remove the coding and you don't allow any base theory that has any logical ideas in it, you really do have a lot of additional challenges. Now, if you go to third order or fourth order or whatever, the challenges exponentiate. I think I'm finished with my speech.
Was there a question also, or?
Okay, here's the question. I have to make it into a question to be legal so I don't get arrested. let me say, are you going to follow the strict reverse mathematics discipline in the future?
If the university upgrades my job from half-time to full-time, I might.
Well, that's very good to hear. I hope they do.
Give them a call. They're very reasonable people.
All right, if you have to give me their email. Okay.
All right, thanks, Harvey. Any more questions?
Looks like no for now, so thanks everyone for this first talk and thanks.